All right, so the first chapter is on temperature. What does temperature mean to you guys?
The amount of kinetic energy in something or energy in something that makes it hot.
When you drive your car, it has kinetic energy, but it's got nothing to do with temperature. Yep.
How fast the particles are moving around.
Yeah. So whenever you talk about temperature, you talk about temperature for thermodynamic systems. Okay. What are thermodynamic systems? Thermodynamic systems are systems which have a large number of particles. Okay. What do we mean by a large number of particles? 50? 100? A million? I'm sorry? So when we talk about this, we talk about systems which have an Avogadro number of particles. What is the Avogadro number?
6.92 times 10 to the 23rd power.
Right. So, a trillion particles. Okay. That's what we mean by a large number of particles. Okay. So systems containing large number of particles. Okay. Can you give me an example of a thermodynamic system? Yeah.
This room.
You are a thermodynamic system. Okay. The gas in this room, the water in this bottle, your table. Yes. So they're all thermodynamic systems. Okay. And the temperature, you will learn, measures the average kinetic energy per particle. Okay. All right. So anyway, so you all know what temperature means. It tells you how hot an object is. Okay. All right. So we'll formalize that knowledge. Okay. Now, the first 4 chapters in this course constitute the subject of thermodynamics. Okay. This will become an entire course in your junior or senior levels. Okay. So it's an very important topic. Okay. So we'll start off by defining temperature and heat in this chapter. Then we'll talk about the kinetic theory of gases. We'll talk about ideal gases. Okay. And relate their kinetic energy and all to temperature, pressure, and stuff like that. Okay. And then we'll talk about the first law of thermodynamics. Okay, that relates how energy transfer can happen via heat and via work. Okay, so for instance, this is a glass of cold water. If I hold it long enough, I'm transferring heat from my body to that. Okay, so I transferred energy via heat. I can also do the following. I can lift the object up. What did I do now? I transferred energy from me to that by doing work. Okay? So anyway, the first law of thermodynamics accounts for all of that. The second law of thermodynamics is related, it sort of is related to the fact how much work you can get out of heat. Okay? So it turns out that you cannot convert all of heat to work. Yeah. The world's most efficient heat engine, for instance, is a sort of a thermal power plant, is about 40% efficient. What does that mean?
It's pretty good. I've seen heat.
It's pretty bad, but what does that mean? 40%.
40% of the heat is turned into it.
So a thermal power plant, you're converting heat to electricity, okay? And about 40% of that heat is converted to electricity. What happened to the other 60%? I'm sorry?
Turned into some sort of.
It remained as heat. Okay? Your car is a heat engine. Okay? It converts, when you burn gasoline, you produce heat, and you convert some of that heat to the motion of the car. How efficient is your car?
Very
Huh?
Not that efficient.
Yeah, well, but you're in a physics class, my friend. You got to put numbers.
30%.
20%.
20%.
So think about this. Every time you put $5 worth of gasoline, you're getting $1 worth of motion. And then this girl here, she brakes every time she sees a squirrel. And she throws out that dollar too. All right, that's life in the fast lane. Okay, so again, the first 4 chapters are thermodynamics. Okay, so again, this whole thing will become a course. You want to learn that. There's lots of slides here, so I'm going to go through them fairly quickly. I'll give you punchlines and stuff like that. Okay. So thermodynamics is a branch that's concerned with heat and its relation to energy and work. Okay. It's a physics of many particle systems. Okay. And when we say many particles, it's we're not talking hundreds or thousands. We're talking trillions and trillions. Okay. So Avogadro's number of particles. Yeah. The laws apply in a wide variety of fields. Okay, so engines, phase transitions, chemical reactions, transport phenomena, and stuff like that. You have to know thermodynamics. Okay. So thermodynamic calculations are essentials for chemistry, chemical engineering, aerospace engineering. So any engineering you do, you need to know thermodynamics. Okay. Now here's the amazing part. So what is a thermodynamic system again? A system containing 10 to the trillions and trillions of particles. Okay. So to describe this thermodynamic system, we'll be using a handful of variables: temperature, volume, pressure, energy, entropy. So here is a 10 to the power of 24 particle system, and you're using 10 variables to describe it. All right? So most of these systems are in equilibrium. We're studying systems in equilibrium, and all you need is a handful of stuff to characterize it. Yep. All right. So we'll study the 4 laws of thermodynamics over these 4 chapters. Okay. The 0th law of thermodynamics states when systems are in thermal equilibrium, we will define that a little more, their temperature is the same. Okay. What does thermal equilibrium mean to you guys? I'm sorry?
The amount of heat put out is the same as it's being received.
That's right. There's no net exchange of heat. Okay. So right now, this faucet is in thermal equilibrium with this table. Okay. There's energy being exchanged, but there's no net exchange of heat. Okay. So for instance, all inanimate objects in this room are in thermal equilibrium. Yeah. Are you in thermal equilibrium with your chair?
If you sit in it long enough.
Huh?
If you sit in it long enough.
And you can sit all as long as you want. Unless you're dead, you're not in thermal equilibrium. So while you're alive, your temperature is higher than the temperature of the seat. Okay? All right. So the first law of thermodynamics expresses the existence of a quantity called internal energy and shows how it's related to distinction between energy transfer as work and energy transfer as heat. I showed you an example. Okay, so we'll come to these again later. So second law of thermodynamics will introduce the concept of entropy. Okay, entropy measures disorder in a system. Okay, and the second law says that entropy of an isolated system never decreases. Okay? So the entropy of the universe is always increasing. Okay? It never decreases. So the third law of thermodynamics talks about absolute zero. Absolute zero is the lowest possible temperature, and you can never get there. Okay, so it's a theoretical concept. Yeah. All right, so you saw that temperature tells you how hot an object is. Okay, and you'll learn next chapter that it measures the average kinetic energy per particle of a system. Yeah. So for instance, here's a metal, okay, and in a solid, these atoms are at fixed location, okay, and what this is showing is this end is hotter than this end. And so what that means is, okay, these atoms have fixed locations, but they're vibrating about their fixed location. Okay, so the temperature measures the average kinetic energy per atom here, and if this end is hotter, these have higher kinetic energy than these guys. Okay. What will happen when this end is hotter than this end?
And the kinetic energy will transfer to the colder.
So energy, heat flows from the hotter end to the cold end, and the way it happens is this guy will bump into him. He transfers some of his energy. He's not going anywhere. And then this guy transfers some of this energy and so on. And that energy is transferred. Okay? Till when will this happen?
Until both sides, until all the particles are the same.
Until the temperature is equal everywhere. Okay? So until the average kinetic energy per particle is the same everywhere. Okay. So here are some. So temperature is a measure of how hot an object is. It's a measure of the average internal random kinetic energy per particle of the system. Okay, and so on. Okay. So here's a couple of interesting numbers. So when the universe began, 13.8 billion years ago, the temperature of the universe was 10 to the 39 degree Kelvin. And today we are bathed, so if this were our universe, we are bathed in electromagnetic radiation, and the temperature of this radiation is 2.73 Kelvin. Okay, that's the cosmic microwave background radiation. Okay. Thermal contact, what does that mean? When are two objects in thermal contact?
When energy is transferred from a hotter object to a colder object.
Whenever two objects can exchange energy, they're in thermal contact. Okay. What are you in thermal contact with?
The air.
Huh?
That's the chair.
You're in thermal contact with everything in this room. How are you in thermal contact with the wall?
Through the air.
I'm sorry?
Through the air.
So convection is one way, but you're also radiating electromagnetic radiation. Okay? I'm sorry?
That's it to the wall.
Yeah. Everything is emitting electromagnetic radiation. And you're absorbing electromagnetic radiation from the wall. Okay. With what is your contact the strongest thermally?
The objects you're touching.
The chair, yep, the objects you're touching. Okay. All right, so thermal contact means that anytime you're exchanging energy, you're in thermal contact with the object. Okay, you can exchange energy via conduction, convection, and radiation. Okay, so heat transfer can happen via conduction, convection, and radiation. Okay. So energy can be exchanged via conduction, convection, or radiation. So the strength of the thermal contact can differ, but okay. Two objects are in thermal contact if energy can be exchanged. So thermal contact and thermal equilibrium. This is a different phrase. What does thermal equilibrium mean?
No net.
No net energy is exchanged. Okay, so you are in thermal contact, but you're neither gaining or losing energy. Whatever you're giving, how much ever you're giving, that's how much you're receiving. Okay, so all inanimate objects in this room are in thermal equilibrium. Okay. you are warmer than all the inanimate objects in this room are about 20 degrees Celsius. What is your temperature?
98.6.
37 degrees Celsius. Okay. All right. So you're constantly losing energy. Do you guys know how much energy you're losing? 100 joules a second. So you're all glowing like a 100-watt bulb. Yep. All right. Two bodies in thermal equilibrium have the same temperature. Okay? And that's the zeroth law of thermodynamics. Okay. So you guys can read that. Okay. Now, what does temperature tell you? How hot an object is. Okay. So we want to be able to measure the temperature of objects. Okay. So we define temperature scales. Okay. And here's an interesting thing about physics. It turns out that some physical phenomena are repeatable. Okay, here's what I mean by that. So let's say if you are at 1 atmospheric pressure, you find that ice will melt. So ice, let's say you're at 1 atmosphere pressure, you melt ice and you put your finger in there and you feel the temperature. It doesn't matter when you do it, in the morning, night, 10 years from now, feels the same temperature. Okay? You boil water at 1 atmosphere, it feels the same temperature. Okay? And so the melting point of ice under 1 atmosphere, under the same conditions, you can call it whatever temperature you want. This feels colder than that, so it makes sense to call this a higher temperature than that. Okay? Okay, so these guys call this 0 degrees Celsius, and these guys call this 100 degrees Celsius. And these guys call it 32 degree Fahrenheit, 212 degree Fahrenheit. And these guys call this 273 degree Kelvin, 373 degree Kelvin. So, how many different temperature scales are possible? An infinite number. Okay? All right, now let me point out something. How many degrees are there between this guy on this scale, between this temperature and that temperature? 100 degrees. How about this scale? 180. Okay. So you see there are 180 divisions between the same two temperatures, 100 divisions between the same two temperatures. So this is sort of a finer scale. Yeah? So this scale was invented when you want a finer measurement of temperature. So this is for weaklings like people. Our body temperature changes by 1% and we cry for mama, right? Your temperature is 99 degrees Celsius and you have a fever. I mean 99, not Celsius, Fahrenheit. Oh man, that was dangerous, wasn't it? So this is a finer scale. So here's an interesting scale. 100 degrees between these 2 points. 100 degrees between these two guys. Seems redundant. So why invent this scale?
Because it starts at absolute zero.
So, okay, so here was the issue. Okay, so temperature measures how hot an object is, right? And tells you the average kinetic energy per particle. So the 20 degrees Celsius in this room, that's the temperature of the air, is telling you the average kinetic energy per particle in this room. Okay, actually, so let me show you a simulation. So here's the temperature of the gas, which is 300 degrees Celsius and 300 degree Kelvin. And so that's telling you how fast the particles are moving. And if I cool the gas, you can see that the particles are slowing down. The temperature is a measure of the average kinetic energy per particle. What is the best you can do in cooling? Stop all the particles, and that's absolute zero. Okay? All right, so we realize that, and eventually on this scale, that turns out to be minus 273 degrees Celsius. Okay? So the coldest possible temperature is minus 273 degrees Celsius. Now that's a very odd number. Explain to your little brother that the coldest temperature is minus 273 degrees Celsius. Yeah? So we'll just call that 0 degree Kelvin, that's all. Okay? So this scale is a rescaling of that, okay? That's all. And so this was first realized by scientists. So you can take a flask and put different amounts of gases in there. So put a gas at 1 atmosphere, 2 atmosphere, 3 atmosphere. And then you start cooling the gas. And you find that this extrapolates to the zero, all gases go to zero pressure at the same temperature. Okay. And when did the pressure go to zero?
Particles stop.
When the particles stop moving, you know? So that's how absolute zero was discovered. Okay. Now, to define a temperature scale, what did you need? I'm sorry?
2 points of reference.
Right, two physical phenomena. Okay, 2 points of reference. So for temperatures that we encounter sort of in our everyday life, these two are good enough. But I mean, we are scientists, and here's two more precise. Okay, what should the reference point be? The reference point should be easily recreatable. I mean, they should be recreatable precisely, very precisely. Okay, so ice will melt at 0 degrees Celsius at 1 atmosphere and so on, and water will boil at 100 degrees at 1 atmosphere. Here are two more precise points. Absolute zero. What is absolute zero? When all molecular motion ceases. You can never get there, but you can define it. Okay, so absolute zero and triple point of water. Okay, so these are 2 points that are physical reference points that are used. Okay? So, and a triple point of water, and I'll come to that in a second. Anybody know what the triple point of water is? I'm sorry?
Point where all 3 states of water exist.
Mm-hmm. So that's the triple point of water, and we'll come to that. All right. All right, so here's a phase diagram. A phase diagram for water, for H2O. These diagrams are very important, okay, and you want to be able to understand these diagrams. What this tells you is, what is this phase diagram telling you? See, on the y-axis is the pressure, and on the horizontal axis is the temperature. So what this diagram is telling you is, okay, so this is 1 atmospheric pressure. At 1 atmospheric pressure and this temperature, this chemical substance can only be in the liquid phase. Okay, so for this parameter space, it tells you what state the substance can be in. You want liquid water at 1 atmosphere and minus 20 degrees Celsius, you're out of luck, my friend. You cannot drink that stuff at 1 atmosphere and minus 30 degrees Celsius. You have to chew it. You know? At this temperature, you can't drink it. You have to breathe it. Okay? So this is a very important diagram. Okay, and you have phase diagrams for all substances, okay? Generally for pure substances. And all right, what does this line tell you?
The point where ice meets water.
Okay, so along this parameter space, along these parameters, the two phases can coexist. Okay, so it also is the melting curve. This is the vaporization curve. And look at this. This is an interesting point, critical point. What this is telling you is, so let's say if you're coming from there, at this point, it's in the vapor phase, okay? And then as you decrease the temperature at constant pressure, you can't tell when the vapor became liquid above that pressure, okay? So that's a critical point. Okay. So here you can tell the phase transition. Here, if you're moving along this line, you can tell you go from vapor to liquid phase. Okay. So about this point, you can't tell. Now, water is an interesting substance. Okay. Most material for solid to liquid phase, their slope is positive, like that. Okay. Now, water has a negative slope, as you can see. Okay. By the way, one thing I should have mentioned is, see the axis is nonlinear. Okay. This is just to illustrate some facts here. All right, so here's one interesting consequence of this negative slope. All right, so we live at 1 atmosphere. Okay? So let's say it snows in Florida. Well, unfortunately, it doesn't happen, but fortunately or unfortunately. All right, so let's say this is minus 5 degrees Celsius. So snow is on the ground. Okay. And you put on your skis and stand on the snow. So when you put on the skis and stand on snow, what happened? You increase pressure. So this was 1 atmosphere, you increase pressure. You melted the snow under your ski. It became liquid, it became grease, and now you can ski. Okay. So, for instance, if this slope had been positive, skiing wouldn't be a sport. You wouldn't be able to ski. Then the only way you would be able to ski is by increasing the temperature. So you would have had to have a heater under your skis to go skiing. All right, anyway, all that aside, phase diagrams are very important, and you need to understand those. Okay? So here's the triple point of water. At this particular temperature, at this precise temperature and pressure, all 3 phases of water can coexist. And then you could go to any phase. Okay, so here's a picture of, and the triple point of water happens to be 0.006 atmospheres and 0.01 degrees Celsius. Okay. So there's vapor, liquid, and solid phase. All right, so we saw that there's an infinite number of temperature scales possible, but the ones in common use are these 3 scales, Celsius, Fahrenheit, and Kelvin scales. And we need to be able to convert temperatures from one to another. And these 2 formulae allow you to convert the temperature from one to the other 2 scales. Okay, so if you have a temperature in the Celsius scale, here's how you use this formula to go to the Fahrenheit scale. Okay? And here's a quick way to do it in your head. So let's say this is almost 2, 9/5 is roughly 2, and then you add 30. So for instance, if the temperature is 20 degrees Celsius, 20 times 2 is 40, 40 plus 30 is 70. Okay. All right, so here's how you go from Celsius to Fahrenheit, and here's how you go from Celsius to Kelvin. Okay? To go from Celsius to Kelvin, you just add 273 degrees to it. Okay. Now, when we do the first and second law of thermodynamics and the kinetic theory, most of the time will be in the Kelvin scale. Okay? So you want to get used to that. So here's, now that we've talked about temperatures, here are some temperatures that we have measured. So the lowest temperature we have reached is probably about 10 minus 10 degree Kelvin. So this is sort of an old thing. Okay, so 0.1 nanokelvin. Okay, so that's actually pretty amazing. So that's probably the coldest temperature in the universe. That's a presumptuous statement. We're saying that there's no other intelligent form in out there, but I'm sure there is. But anyway, so imagine this. So a sample like that, about that big, we have cooled to 0.1 nanokelvin, 100 miles from here at UF. And that potentially is the coldest temperature in the universe.
How'd they do it?
Well, so how do you cool something?
Flow on,
Huh?
flow on. You remove energy.
Get a freezer?
I'm sorry?
Freezer?
Get a freezer. All right. So heat will, which way does heat flow?
From a warmer object to a cooler object.
And from a warmer object to a colder object. All right, so here's a colder object and heat will flow this way. So this is hotter, this is colder. Okay, so you have to keep, you want to cool something, you have to bring something cooler to it. Okay? Okay. So there are various techniques for doing it. Okay. So for instance, okay, so I'm going to tell you a couple of ways of doing it. Again, cooling something is a multi-step process. Okay. So let's say, so here's liquid helium at 4.2 degree Kelvin. Okay. And what if you attach a vacuum to it, if you reduce the pressure, liquid helium will vaporize and the temperature will drop. Okay, so when something vaporizes, it drops. Let's take a bunch of magnets. Okay, and we have a magnetic field like that. If all the magnets are lined up like this, this is essentially 0 degree Kelvin. So if it's not 0 degree Kelvin, what happens? Then some of them are lined up in this direction. This is a hotter temperature. Okay, and if 5 are lined up like that and 5 are lined up like this, again, this in principle is infinite degree Kelvin. Okay. So if you have a bunch of magnets and they're lined up like this, okay, whatever, this corresponds to a temperature. And what you can do is you turn on a magnetic field. When you turn on a strong magnetic field, some of them will switch in that direction. Okay, let's say you switch them. Okay, now this is, and now you turn off the magnetic field. Now what is this? This is a lower temperature sample. And now you attach it to whatever it is that you want to cool down. Okay. So it's a long process. Okay, but there are ways to cool stuff down. Okay. Again, so getting back to this, here's an amazing fact. So these guys 100 miles from here, you can find the coldest temperature in the universe. Okay. All right. but we want to make sure we understand an important point here. Okay, so the surface of the sun is about 5,600 degree Kelvin. Okay, how do we know that? Did Brock put his finger there?
Hopefully not.
Hopefully not. Well, we know for sure not. How do we know the temperature of the surface of the sun?
We measure the amount of energy emitted.
What energy? So, surface temperature of the sun. Here's, look at this. The interior of the sun. That's 15.6 million degree Kelvin. How the heck do we know that? So this is the surface temperature of the sun. All right, so here's how you measure. If you don't want to stick your finger on something and you want to know its temperature, what you want to do is, here's what you do. Okay, so every object emits electromagnetic radiation. And this radiation has a particular characteristic. Okay? Well, what do I mean by that? Okay, so let's go back to our simulation. Okay, so there is a black body spectrum. Okay, so if you have a solid or a liquid, okay, what this tells you is, okay, so see, here's the temperature. Oops, this is the temperature. Okay, I change the temperature of this object. So if the temperature of this object is that, what this graph is telling you is, see, this is the wavelength, and that is the intensity at that wavelength. Okay, so for solids and liquids, that is at this temperature, at this wavelength, it will emit that intensity. At this wavelength, it will emit that intensity. Okay, so this graph, okay, the spectral distribution is unique for temperatures. Okay. You guys have been to a doctor's office and they measure your temperature using a thermometer like that, and that's what they're doing. Okay, what they're doing is they're measuring the intensity at 3 different wavelengths, and then they fit the curve. Okay. So this is how you know the temperature of the surface of the sun. You just go outside, measure the intensity at 3 or 4 different wavelengths, and you get the temperature of the sun. That's how you get the temperature of all stars, surface temperature of stars that are far, far away. So you're measuring the electromagnetic radiation intensity. How do we get the temperature of the inside of the sun, of the core of the sun?
We created a fusion reaction ourselves.
No.
Yes.
So, yeah, but how do you know you're getting the same temperature as the temperature at the core?
Because the reactions happen in the core of the sun.
Yeah, but all different stars have different core temperatures. So, you want something that is coming from the center of the sun that is not being disturbed. Okay? And it is related to fusion reactions. And in the fusion reaction, something called neutrinos are emitted. And these neutrinos interact with matter very weakly. So essentially, they're coming through the sun undisturbed. Okay? So you're measuring that curve for the neutrinos. Okay? And so that's how we know the temperature of the core of the sun. Okay? In fact, trillions of neutrinos are passing through your body right now, every second. Okay? And they weakly interact, and so they don't harm you. Okay? All right, so anyway, the important thing is the temperature of remote objects are measured using from the black body radiation spectrum. Okay, so that's how you get the temperature of a furnace, for instance. Okay, nobody sticks their hands in a furnace. Okay. All right, so here's an interesting little chart. See, human experience is in a tiny window. Okay, so that's the temperature range. Again, the center of the sun is 15 million degree Kelvin. We are building a fusion reactor, the largest tokamak in France, and hopefully it'll produce electricity in 10 years. Okay. That'll get to 100 million degree Kelvin, 10 times hotter than the sun. But that's nothing. Okay. In reactors, we have collided heavy ions, and the temperature there has at the collision center has gotten to trillion degrees Kelvin. Okay. But again, this is nothing compared to the temperature at the Big Bang, which is 10 to the 39 degree Kelvin. Okay. Anybody need a break? All right. All right, so let's say this is a metal. It's a solid, so, and the way it's modeled, the atoms are in fixed locations, and the forces between these atoms are modeled by this spring. Okay. So now let's heat this metal. What will happen?
Cause the atoms to move around.
Yeah, very good. So the atoms will vibrate with greater amplitude. Their average kinetic energy will increase. What else will happen?
The springs will expand and contract.
Yeah. So here's the deal. So when you heat, you're supplying energy, and you're supplying equal amounts of energy to all degrees of freedom. Okay. It's not like I give him $10 and I give him $5. Okay. I give him equal money to everybody. Okay. So you add kinetic energy, you add potential energy as well. So this average distance between atoms will increase. All right, so what is the net effect in a macroscopic sample? So when you heat the sample, the average distance between every atom has increased. So if the length of this rod will increase, okay, its width also increases. So, but right now, if the predominant dimension, the greatest dimension is the length, let's just study the increase in length. Okay. Okay. So, and this is of practical importance to us. So we'll study this. So let's say you've taken a metal rod, you've heated it, its length has increased. Okay. And so the increase in length is proportional to the original length. The longer the object, it's proportional to the original length. It's proportional to the increase in temperature, and it depends on a number that depends on the material. Yeah. And that is called the coefficient of linear expansion. Okay. So let's see how big this number is. Okay. These numbers are important enough that they give you tables for them. Okay. So if you're a material scientist, well, I mean, if you're any kind of engineer, you'll be interested in this. So coefficient of linear expansion for aluminum is 25 times 10 to the minus 6. What this means is the following. So let's say this is 1 meter, and we heat an aluminum rod by 1 degree Celsius. Okay. And the increase in length will be 25 times 10 to the minus 6, which is roughly 2 parts in 100,000. So you take a 1 meter aluminum rod, 2 parts in 100,000 is 2/100th of a millimeter. Okay, again, 2 parts in 100,000. Why do you care about that? Right?
You build buildings.
What's that?
You build buildings out of aluminum, and if it gets to, like, say, an extremely hot day,
Uh,
you know, and temperature rises, you don't want your aluminum structure of your building to snap because the rod's gonna.
Right, so, okay, so now every bridge has these expansion gaps. Okay, so if these expansion gaps weren't there, you build a bridge with one long metal rod, it would buckle in the summer. It would expand and push against that, and it would buckle. Okay, the forces would be too great to, and it would buckle. Okay, so every bridge has an expansion gap. So here's a bridge in Michigan. It's about a mile long, and between winter and summer, it expands by 1.5 meter. 1.5 meters is your height. Okay, and if there were no expansion gap, this would collapse. All it takes, so all it would do is last 1 year. So there are these expansion gaps. So this is the between spans. So this is the state in winter, and this is the state in summer. You've seen this everywhere. The sidewalks, those cuts on the sidewalks, those are expansion gaps. Yep. Train tracks, so every rail is about, I think, 25 meters, and then you have to leave expansion gaps for the summer, okay? And so this is what happens if you didn't leave enough expansion gaps. Yep. So somebody messed up here, okay? You guys might have heard of the Trans-Siberian Railway, which is 10,000 kilometers across, twice the distance from the east to west coast. And the expansion gaps add up to 8 kilometers. 8 kilometers is from here to Ormond Beach. All right, so now here's an interesting question for you guys. All right, so here's a washer. Let's say this is made of steel, and you heat it, the steel will expand, okay? The question is, how does this gap expand? Do you guys understand that? Okay, so if I had a solid spherical steel washer, you know how the steel would expand. But the question is, how does this gap expand? It turns out that the gap will expand the same way as whatever material is surrounding it. Okay, so to see that, imagine this solid steel circle, and you heat this outer ring will expand, and the inner ring will expand as well. Okay.
Does
So,
it have anything to do with the pressure of the screw?
I'm sorry?
Does it have anything to do with the pressure of the screw? Like
Pressure of the, no.
the screw being in the washer?
No. Okay, so the gap expands the same way as the surrounding material. Okay, anyway, here's a little trick that people use for ball socket joints. So ball socket joints, of course, you start out with a ball that is bigger than the socket, and then how do you join it? So you heat the socket, expand the hole, and get the ball in. Okay? And then when it cools, you got a ball socket joint. Okay. Here is an interesting application as well in in aeronautical engineering. Planes are, the fuselage is made of, what's the fuselage made of? Aluminum. Okay? Aluminum is pretty soft. And so you got to screw these panels together. You want to screw aluminum panels? You're going to wear out the threads, right? So how do they do that? So you take aluminum screws, cool them, and put them in the socket, and when they come to the normal temperature, they'll expand. Do you guys understand?
Yeah.
Mm-hmm. All right, so again, gaps. So area expansion is 2 alpha times A times delta T. Volume expansion is 3 alpha. Beta is 3 alpha. So the volume expansion is beta times original volume times rise in temperature. Okay? So again, when you heat something, what happens? The average distance between atoms increases, and so you have Length increase, area increase, and volume increase.
Oh, could you go back? I'm sorry.
Yeah, no worries. Okay, so again, I know this is dense material and stuff like that, but I'm recording as well, so if we don't take a break, that'll be good for me. All right, I don't want to break it up into two files. But if you absolutely need a break, we can take a 30-second break, you know. There'll be a pause in the recording. No big deal. All right. So let's check something out. Rho is the density of a material, mass divided by volume. So here's some material. I'm going to heat it. When I heat it, its temperature rises. What happens to the volume? Increases. What happens to density? Has the mass changed when you heat it? No. So volume increased, density decreased. So for most materials, you increase the temperature, the density decreases. Right? All right, let's look at this graph. Here's the graph for fresh water. Here's density. You're increasing the temperature. Okay, so let's look at this part of the graph. You're increasing the temperature and the density is decreasing. So water is behaving normally. But let's look at this small window. You're increasing the temperature and the density is increasing. Crazy.
Why?
What's that?
Why?
Yeah, so it's a property of water, so, okay. You're increasing the temperature and its volume is decreasing. Now it's a very small effect. See, it's a 1 part in, so this is 20, it's 1 part in, it's 20 parts in 100,000, 1 part in 10,000 effect. Okay, but this is extremely important for life. So let's see that. You guys understand? So let me tell you the story about that. So here's a lake. Let's say we want to freeze the lake. How do you freeze the lake? I'm sorry?
Just cool the.
So you have to remove heat from the lake to freeze it.
Yeah.
And to remove heat, you gotta bring something colder in contact. So what you do is you just go home, flip a switch, turn the air temperature to minus 20 degrees Celsius. All right. You don't have that switch at home?
I do.
Yeah, I knew. That's why we let you in this class. All right, so heat flows like that. So this water was at 10 degrees Celsius. What happens? This will cool down. This cools down to 4 degrees Celsius. Okay? And you just saw that at 4 degrees Celsius, the water is densest. Okay? So this water that's the densest will go down. Okay? So this will go down and this is 4 degrees Celsius. Okay, eventually, so the 4 degrees Celsius water is at the bottom. Now, heat is still flowing out, this temperature is still that, so this will be 2 degrees Celsius. But this water doesn't sink because this is lighter than that water. It'll cool down to 0 degrees Celsius, okay? And it still won't sink, okay? And it'll freeze. Now, ice is lighter than water, so that will float. Okay? And ice is a poor conductor as well, so now heat flow is minimized. Okay? So now, unless you keep this for an infinitely long time, you don't do that in nature, because in a few months summer comes along, and this temperature warms up. Okay? So, in practice, you can never freeze the entire lake. Okay, this remains water, and the fish can live in that water. So you see, this guy, this little bump in the graph was crucial for life up north. Okay? All right. So again, anyway, little things in nature, it's amazing how useful they are. Yeah. And all right, now we'll talk about heat. So again, we've been talking about heat. You know what it means to heat an object, and when you supply energy, what you're doing is you're adding kinetic energy, you're adding potential energy. Okay, so this kinetic energy is random, the potential energy is random, it expands in every direction and so on. Okay, so heat is the internal energy transferred between objects because of temperature difference between them. Okay, internal energy or thermal energy of a system is the random kinetic energy plus potential energies of the microscopic constituents of the system. Okay. So internal energy is all that random kinetic energy and potential energy. Now, if you have a complex molecule, you'll have rotational energy as well. Okay, so all those internal energies add up to internal energy. Okay, so when this object is hot and that object is cold, all this internal energy goes to that object. So the kinetic energy is decreasing, the potential energy is decreasing, the rotational energy is decreasing, and all kinds of energy. Okay? All right, so that's heat. Okay, back in the old days, 300 years ago, they didn't know that heat was just another form of energy, just potential, kinetic, and all that kind of energy. Back 300 years ago, they thought it was some kind of fluid, okay? And they had defined a unit for heat. A calorie was the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's how it was defined, okay? Now, once they realized that heat is random kinetic and potential energy and all, they wanted to know how many joules is 1 calorie, okay? And Mr. Joule did this experiment. So what he did was he took this weight, and when this weight drops, when the weight drops through a height h, the energy it loses is mgh. And this you can calculate in joules. Okay? And what happens when this thing drops?
Paddle spin,
The paddle spins,
which heats the water.
it warms up the water, and you can measure the temperature of the water. And that you can calculate in calories. Mass of the water, mass of the water times specific heat of water times change in temperature. You can calculate this in calories. Okay, so from this experiment, Mr. Joule was able to calculate how many joules is 1 calorie, or how many joules is 1 calorie. Okay? So this is known as the mechanical equivalent of heat, and 1 calorie he found was 4.184 joules. Okay? And this and many other things is why we named the unit of energy as joule after Mr. Joule. Okay? Okay, so if you add heat to a substance, what happens?
Its temperature increases.
Its temperature increases. Okay. So how much does its temperature increase? So if you have a solid or a liquid, to measure the amount of stuff, it's easiest to measure the mass of the stuff for solids and liquids. Okay. And depending on the solid and liquid, so this is how much heat you've added. This is the mass of the object. That's something called the specific heat of the mass of the solid or liquid times the temperature rise. And so you can see if the specific heat is high, the temperature rise is lower. Okay? Now for a gas, it's easier to measure the number of moles of gas rather than the mass. Okay? So we define molar specific heat for, so this is molar specific heat for gases. Okay? So this is called specific heat, and that's called molar specific heat. Okay? So for gases, it's easier to measure the number of moles, and M is the mass for solids and liquids. Okay, so here's again, all these properties are important, and we have a list of stuff. And notice, so this is the specific heat. What it tells you is joules per kg per Kelvin. What it tells you is if you take 1 kg of the material to raise its temperature by 1 degree Kelvin or 1 degree Celsius, you need that many joules of heat. And notice, see, for water, the specific heat is so much larger than for other materials. So for lead, it's that. So for water, the specific heat is 40 times greater than for lead. You take 1 kg of lead and raise its temperature by 1 degree Kelvin, you need 100 joules of heat. You take 1 kg of water to raise its temperature by 1 degree Kelvin, you need 4,000 calories, joules. Okay? All right, dirt is essentially silicon dioxide. So specific heat of dirt or land is that, roughly. Look at that. For water, 6 times greater than dirt. And so here's what happens. All right, so again, let's look at this formula. Q is mc delta T. Okay, let's say you have the same amount of heat falling, same amount of mass. If the specific heat is higher, the temperature rise is lower. Okay? So let's say this is land and water, and during the day, same amount of heat is falling. Okay? So the specific heat of water you just saw is 6 times greater than that of land. During the day, the land gets much warmer. Yeah. The land gets much warmer, the air over the land gets much warmer. Air expands and rises. So now you have a low pressure at the air in land. Okay, so this warmer air rose, there's a low pressure here, there's a high pressure here. And so you get a breeze blowing from a high pressure to a low pressure.
And C stands for specific heat, correct?
Yes, C stands for specific heat. Okay. At night, what happens is the heat content of the land is less. It cools much faster. The water is still warmer. And now this air rises. And the pressure here is higher. The pressure there is lower. And so you have a breeze this way. Yeah. So that's why property on water front property is expensive, because you always have a breeze. You know? And you can go to the ocean and come 3-4 kilometers inland, the temperature difference is 3-4 degrees. Okay, so let's say, now, let's say you get a bunch of ice from your freezer and put it in a pan and put it on your range. You heat it. The ice from your freezer is at -5 degrees Celsius, but we'll say it's at 0 degrees Celsius. What happens? Oh, actually. All right, let me go back to minus 5 degrees Celsius. Now what happens? So we are doing this in Florida. And the pressure is 1 atmosphere.
And you said if you put the pot of ice on the stovetop
Mm-hmm.
at -5 degrees Celsius.
Right.
And the stove's not on, it's just,
I'm sorry?
the stove isn't on, right?
Yeah, no, it's on.
Oh,
It's on.
Oh, oh,
No.
it,
The particles start moving and it melts.
All right. So none of it will melt. The temperature of ice will rise to 0 degrees Celsius. And now, when it's risen to 0 degrees Celsius, the temperature won't rise. The ice starts melting.
Oh, I got you. It's still in the ice state during the 5 to 0, and then
Mm-hmm.
then one of
from
them
0
is,
up. I got you.
Okay. So right now, all the heat is going into raising the temperature. Once phase transition starts happening, none of the heat is going into raising the temperature. It's all going into melting the ice. So as long as you have ice, all of the heat is going into melting the ice. Once all the ice is melted, now you can raise the temperature a little. Okay? So this heat that went into not raising the temperature, but went into changing the phase of the material, that's called latent heat. Okay? So latent heat is the heat supply that is not changing the temperature of the object. Okay? All right. So, well, what's going on? So when the ice was at -5 degrees Celsius, you heated it, the molecules were going faster because it was warming up. Okay? But when it was melting, so ice at 0 degrees Celsius, these atoms, these molecules have the same kinetic energy as the melted water at 0 degrees Celsius. Okay, so the latent heat went into breaking these bonds. It didn't go into speeding up the molecules. Okay? And so as long as you have the solid phase, as long as ice is at 0 degrees Celsius, you heat it, all that heat is going into breaking the bonds. Okay. So here's a good number to remember. The latent heat of fusion, when you're melting something, it's called latent heat of fusion. It's 80 calories per gram. What does that number mean?
it takes 80 calories in order to change 1 gram of thing,
Ice to water.
right? Ice water.
To melt 1 gram of ice to water, you need 80 calories of heat. Okay. And so if you wanted to freeze 1 gram of water, what do you have to do?
Subtract 80 calories.
Right? You have to remove 80 calories per gram. Okay. So when you go buy an ice bag of ice, that's what you're paying the money for. The electricity to draw that heat off. Okay. So if somebody didn't price the ice right, their electric bill is greater than their revenue. All right, so similarly, now let's do the other phase transition. So this is solid to liquid phase transition. Now what we'll do is we'll boil water. Okay, so 50 degrees Celsius, it rises to 100 degrees Celsius, and then once water starts boiling at 1 atmosphere, okay, so all the heat that's you're supplying is not raising the temperature, but it's going into phase change. Okay, so liquid to gas phase change. And then once you convert all of it to steam, then you can raise the temperature of steam to anything you want. Okay? Well, not really. I mean, eventually it won't be water. It'll all dissociate, ionize, and stuff like that. But while phase transition is happening, you're not changing the temperature. Okay. The latent heat of vaporization of water is 540 calories per gram. Okay, so this is a good number to remember, and this is a very important number to remember. So 540 calories, what does that mean? To convert 1 gram of water to steam, you need 540 calories of heat. Okay. So here's something that you hear. Okay. So 1 gram of water at 100 degrees Celsius and 1 gram of steam at 100 degrees Celsius. So same temperature. What would you have thrown at you? What? Neither, of course, but if you didn't have that choice.
Well, the steam,
Huh?
The steam.
All right, so if steam gets thrown at you, that steam becomes water. It burned with you 540 calories, and this is still water at 100 degrees Celsius. That's why they say you don't want steam burns. Okay.
1 gram of steam is a lot of damn steam, I guess, right?
What's that?
I said 1 gram of steam is a lot of steam, isn't it?
All right. All right, did you guys understand that? Okay.
What does LV stand for, like latent,
Latent heat of vaporization.
okay,
Okay. All right, so latent heat go into breaking those bonds, okay, and so the molecules are still, so this is ice at 0 degrees Celsius, the average kinetic energy is the same as the average kinetic energy of water molecules at 0 degrees Celsius, okay. So latent heat is how much substance has changed phase times the latent heat, okay. So again, this is ice melting. When ice is melting, the temperature remains constant, and then once all of ice is melted, you can raise the temperature of water. So next time you see a glass of ice water, you don't have to measure its temperature. You know it's at 0 degrees Celsius. Okay. So these are again latent heat of fusion. That's when solid to liquid phase change. Latent heat of vaporization. This is liquid to gas phase change. Okay. And there are the numbers for various stuff. And I'll quickly go over applications. Okay. Does anybody need a break? The recording will just have a pause. All right, quickly, you have 1 minute break if you guys want to go.
Good.
Good?
Yeah.
All right. All right, so we're all warm-blooded, and our body temperature is 37 degrees Celsius, roughly 98 degrees Fahrenheit. Okay, and like I said, your temperature rises by 1 degree Fahrenheit and you feel like crap. 1% change. Okay. So you, under different conditions, you maintain your body temperature. Okay. How do we do that? So we'll talk about that. Okay, so here's something you need to know. Reaction rates double every 10 degrees Celsius. Okay, now your body, there's millions of reactions going on and they're interdependent. Okay, so if you make something, all reactions are supposed to get a certain rate and stuff. So you raise the temperature and the reaction rates will become different for different reactions, and things can get messed up. Okay. Well, what does this mean? Reaction rates double every 10 degrees Celsius. So here's what that means. So let's say you're boiling potatoes. What temperature does the water boil at? 100 degrees. And this cooks in 30 minutes, or we'll say 40 minutes. Okay. Now, if you could cook the potatoes at 110 degrees Celsius, how long will it take to cook?
I'd assume 20 minutes.
Very good. You've gone to college, I can see. 120 degrees Celsius. Hmm? 10 minutes. You can cook stuff faster if you cook at a higher temperature.
Wouldn't that mess up the food though?
I'm sorry?
Wouldn't that mess up the food though?
Depends on if you're going Ramsay or not.
No, I mean, okay, so you've done pizza in an oven, 350 versus 425. It doesn't. You just.
I mean, the crust is gonna be pretty messed up, I guess, right?
What's that?
It'll be a lot crispier, the crust.
Well, I mean, if you leave it longer, but you can cook it faster.
I got you though. I don't know.
All right. Anyway, so how do you cook potatoes at 120 degrees Celsius? Okay, so water boils at 100 degrees Celsius at 1 atmosphere. At 2 atmosphere, it'll boil at 120 degrees Celsius. So if you put a lid on that and build up the pressure to 2 atmospheres, that's a pressure cooker. Okay, water there is boiling at 120 degrees Celsius. Okay. All right, anyway, so like I said, that thermodynamic system sitting there is a complex set of reactions, and it wants to maintain a constant temperature. Okay, so here we go. So here's the problem. This is a air conditioning problem. Okay, so like I said, you're a 100-watt bulb. So you guys sitting there, if you don't want to raise your temperature, what is it that you have to do? You're producing 100 joules of heat per second. You have to get rid of 100 joules of heat per second, right? And that's how you maintain your constant temperature. Now let's say you go for a run. And now suddenly you're producing 10 times the heat. Your air conditioning system has to crank up by a factor of 10. How do we do that? Did you guys understand the problem? So here's how you do it. Yeah. So here you are. What you do is you are smart and you decide to sweat. Are you cooling now? That doesn't cool you. What you hope is that the humidity is less than 100% and the sweat evaporates. And that's where this number comes in, 540 calories per gram. Okay. When every gram of sweat evaporates, it takes away 540 calories of heat. That's your air conditioning system. Yeah. So you don't want to put a treadmill in a sauna because your sweat won't evaporate. Yeah. Okay, so biology takes advantage of those latent heat numbers. Okay? Here's something that I read in a book. It was actually one of our colleagues. Apparently, and I don't know if this is true, but it was in that book. So here's this guy, here's a steak, 260 degree Fahrenheit. They're both going at the same time. The steak cooks, and this guy is able to walk out, apparently. He probably doesn't have the appetite to eat the steak, but your cooling system is very efficient. Okay. What's that?
I was asking if you wanted to be the test subject.
I see. All right, we're going to go faster, but now, so again, what are we are illustrating the latent heat of fusion and vaporization for water. Again, what is the latent heat of fusion for water? I'm sorry? 80 calories per gram, okay? So you want to melt 1 gram of ice, you have to add 80 calories of heat. If you want to freeze 1 gram of water, you have to remove 80 calories of heat. Latent heat of vaporization is 540 calories per gram. Okay. All right, so here is one of the lakes, and in the winter, a layer of ice as 150 centimeter thick layer of ice, your height forms. So you have to make a lot of ice. How do you make ice? You have to remove heat, right? For every gram of ice, you have to remove 80 calories of heat. Okay. To freeze this lake, this is half of Florida. How much ice do you have to remove? Heat do you have to remove? The heat contained in 10 million atom bombs. Again, how do you freeze a lake? You turn the temperature of the air to minus 20 degrees Celsius. So how much heat has flowed out? 10 million atom bombs worth of heat has flowed out. And the ice melts in the summer. So this much heat was removed, and back in the summer, all that heat was put back in. And that's just one lake. So nature moves a lot of heat back and forth. All right. So heat transfer. When does heat transfer occur? Where does heat transfer occur? From a hotter object to a colder object. Okay, and heat transfer can occur one of three ways: conduction, convection, or radiation. Okay, so here's a fire. You feel the heat. This is via radiation. You can put a metal rod in there, and heat will be conducted there, so you can get some heat there. Okay, and this is mostly convective heat. What is happening is this fire is warming the air, and that warm air is rising and getting the heat. All right. By the way, so for convective heat transfer to happen, you need to be in a gravitational field. So this is how a flame looks like on Earth. There's no the gradient is much smaller in space, and so this is how a flame looks like inside a space shuttle. Okay. All right, conductive heat transfer again. Here's a solid. These molecules or atoms are vibrating with the larger amplitude. They transfer some of their energy to them, these to them, and then, okay. And that's how heat transfer happens. And in a metal, there's free electrons, and the free electrons act like gas. They also conduct heat. But all right, so that's how. So the particles themselves are not moving, but they're transferring energy to their neighbors. Okay, and that's how energy is transferred. Okay. What we are interested in is the rate of heat flow. Okay, so for instance, right now it's cold outside, and we're maintaining a warmer temperature inside, and heat is flowing out to the outside. What does that mean? That means our electricity bill is going up. Do you guys know how much we pay at the Daytona State College in electricity? $500,000 a month on the 6th campus. Our electricity bill is about $6 million. Okay. So to cut down our electricity bill, you want the heat flow to be smaller. Okay, this is the thermal conductivity. So what do? You want the materials whose thermal conductivity is smaller. You build metal walls, and your electricity bill will go up. Okay? And that's the area across which heat is flowing. And that's the temperature gradient. That's the temperature difference and the thickness of the wall. Okay, so you can make thicker walls, and your heat flow will decrease. Okay? All right. Anyway, heat flows from a higher temperature to lower temperature, so the temperature decreases in that direction. That would be negative. So you can write the power rate of heat flow in terms of the temperature gradient. You know? Again, K is the thermal conductivity of the material. You know? So here's another engineering application. Okay. How much heat are you producing?
80 calories.
I'm
80 calories.
Yep, you're a 100-watt bulb, 100 calories a sec, 100 joules a second. This damn thing, this thing is also producing 100 joules a second. Okay. Now, in a server farm, so one CPU is roughly 100 watts. In a server farm, you could have a room twice this size or whatever, have 10,000 servers in there. That's 1 megawatt of heat. So a couple of rooms, and you're producing as much heat. A home is roughly a kilowatt. 1,000 homes worth of heat. If your air conditioning goes down, his millions of dollars serving on that server will go up in flames. Right? Okay, so you have to learn to cool those server farms. Individual CPU is there's a CPU. It sits on a metal thing, and then you blow air through there. That's how you cool the chip. Okay, so this is okay, I got 20 more minutes. Okay, I gotta finish this. Okay, convective heat transfer. In conductive heat transfer, molecules do not move, they just bump into neighbors. Okay, here's convective heat transfer. You want to heat up a room, you turn on the heater, this warms the air around it, a fluid around it, and that fluid expands, gets lighter, rises up. Okay. And then cold air gets here, and then it circulates, and that's how heat is transferred. Okay, so eventually the entire room will get warm. Okay, so convection is very important to us. So here, this is the waters near the equator, and those get warm from the sun. Okay, and this warm water, so this warm water travels to the north. Okay, so you can see that this is the Gulf Stream. Okay, this is warm waters flowing north, and they flow at about 5 to 6 miles an hour. And this is how it was discovered. Mr. Ponce de Leon was sailing in this direction. The winds were behind him, and he was going nowhere. And that's how he discovered the Gulf Stream. Okay. The Gulf Stream is about 100 kilometers wide. As you can see that it's as wide as Florida, and about a kilometer deep. So the oceans are about 4 to 5 miles. So roughly, so quarter of the ocean depth. Okay, so it's a river, warm water flowing, and this is the temperature is about 20 degrees Celsius. Okay, so there's a lot of water flowing. And you guys can read about this. So the water flowing in this Gulf Stream, the volume Gulf Stream dwarfs all rivers that empty into the Atlantic combined. So the Mississippi, the Amazon is not even close to how much water is. So this thing is, the water here is 300 times the water from the Amazon and the Mississippi combined. All right, so you learned about conductive heat transfer, you learned about convective heat transfer. Convective heat transfer, a fluid is carrying the heat and transporting it by moving. Okay? In conductive heat transfer, nothing is moving, it's just energy is being transferred to the neighbors. And the third mode of heat transfer is radiative heat transfer. every object emits electromagnetic radiation. Okay? The power radiated, that is the amount of energy radiated. Power is energy per second. Radiated depends on the surface properties of the material. It's called the emissivity. This is a constant that's the same for every object. That's called the Stefan-Boltzmann's constant. That's the area of the object. That's the temperature of the object in Kelvin scale. Okay. Babies have a larger area to volume ratio. Okay, so they can lose a lot of heat radiatively. Okay. Yeah, so you see in this picture, what is this picture showing you? This is radiative heat transfer. All the warm air is in your attic, and that's where you lose a lot of heat from. Again, so that's why they put a lot of insulation in attics. Yeah. Okay, this illustrates that everything emits radiation. You are emitting radiation, except that we at our body temperature, we are mainly emitting in infrared. Okay, so what this is illustrating is the following. So here's this guy, his arm is covered. Okay, he's emitting infrared radiation. Okay, and infrared radiation is being blocked by this plastic. Okay, so no, it's not being blocked. So if you take a camera that's sensitive to visible light, you can't see his arm. But if you take a camera that's sensitive to infrared light, you can see the arm. Okay. All right, what this is telling you is the net amount of radiation. So you're emitting a certain amount of radiation based on your temperature. You're sitting in a room whose temperature is that. Okay, so if you were sitting in a room where the temperature is the same as your body temperature, there would be no net radiation loss. But the wall temperature is lower, and so you're losing net amount of heat. Okay. Okay. It turns out that dark surfaces are good absorbers. Good absorbers of radiation are also good emitters of radiation. Good reflectors are poor emitters. Okay. So in the winter, you want to wear dark clothing, and in the summer, you want to wear light clothing. Are you tired, or you guys want to see the other slides? Hmm?
Yeah, let's. Are you tired?
Hmm?
Are you tired?
No, I can keep going. All right. Okay, so this was the Big Bang. And the universe was expanding. And as it was expanding, it was cooling. So let's say this is 100,000 years old universe. Okay, so what it had was a bunch of protons, electrons. So I'm not telling you this part of the story. All right, a bunch of photons and stuff like that. Okay, what does the temperature tell you? I'm sorry? How hot an object is. It's telling you the average energy of the photons and the protons and the electrons. Okay. Do you guys know the ionization energy of hydrogen? I'm sorry? So I'm going to ask you this again next class, and you're going to remember it, right? Of course. Okay, so this is the ground state of hydrogen, and 13.6 electron volts is the ionization energy of hydrogen. Okay. All right, so we are 100,000 years after the Big Bang. The average energy of this thing, these photons, is greater than that. Okay, so if a hydrogen atom formed, these photons would ionize the hydrogen atom instantly. So atoms couldn't form. Okay. So whenever you have these free charges, these photons are bouncing off these free charges. Okay, they're scattering. Okay. So now let me tell you. So let's imagine a very foggy day, extremely foggy day, and you have a car coming with its headlights on. Can you see the headlights of the car?
You can see the headlights, you can't see it.
Right. So, I mean, all the lights get scattered and you can't see the image. Okay. Let's say the fog suddenly comes off. Now you can see the light. Okay.
Unless they have the brights on.
I'm sorry?
Unless they have the brights on.
All right, so the universe is expanding. Radiation is cooling down as well. Its energy is decreasing. Okay, so now at 380,000 years, the energy of the photon is low enough now, it can't ionize hydrogen. At 380,000 years after the Big Bang, the first atoms formed. The fog lifted. And now that radiation can travel for free. And the universe has still been expanding for another 13.4 billion years. Okay, and this thing has cooled down. So today the universe is a little bigger than that. Okay. Okay, so here's the universe today, and that radiation that has remained and that's free traveling, we can see this radiation as the cosmic microwave background radiation. Okay, and the temperature of this radiation is 2.73 degree Kelvin. Okay. Back then, the temperature of that radiation was 3,000 degree Kelvin. So it's cooled down by a factor of 1,000. Okay? And that is the radiation that these guys discovered. Two guys in Princeton discovered in 1965. And that's this image that you see. This is the cosmic microwave background radiation. So this is the galactic North Pole, South Pole. All that means is, where do we live? We live in a spiral galaxy. Okay, so that is the radiation looking, this is the radiation looking in that direction, this direction. Okay. All right, so what this is telling you is, so again, the temperature is 2.73 degree Kelvin. Where is the temperature? Yeah, there is a 2.73 degree Kelvin. And so when we initially measured, it was 2.73 in every direction. But then if the temperature was uniform, then galaxies couldn't form and stuff like that. And it's the colder spots that where galaxies form. Okay, so it was important to detect this variation in temperature. And eventually we did. We sent satellites and all that. And we discovered the variation. Okay, I'm going to tell you one more fact and then we'll end at that. Okay. You have to know this since you're young, the greenhouse effect. Okay, we get our energy from the sun. The sun is sending mostly visible light. And near our atmosphere is transparent to visible light. Okay, we absorb half this radiation, half of it gets reflected. And then we re-emit this as infrared radiation. Now our atmosphere has different properties to infrared radiation. Now, if you don't want the Earth to warm up, whatever energy you're getting per second, you have to emit that much energy per second. Right? So, till the 1800s, 1850 and stuff like that. In the 1800s, 1850, let's say, the temperature, average temperature of the Earth was 14 degrees Celsius. Now, in the last 50, 60 years, in the last 70, 80 years, the amount of radiation being emitted is less than the amount coming in. Okay, so how much is it less? It's 3 point, today you can look up, there's a link, radiated forcing link on a Wikipedia page, you can go there, watts per meter square less. So here's a meter square, you know 3.4 watts. So for every meter square of the Earth, we are radiating 3.4 meters less, and 3.4 watts less. And so we are warming up. Today the temperature is 15.3 degrees Celsius. For your sake, I'll be dead by then. So for your sake, we hope that the temperature is less than 16 degrees Celsius. Okay, why are we trapping heat? So if you dump carbon dioxide in the atmosphere, carbon dioxide absorbs infrared light. Okay? So there is the Earth. You emit infrared light, carbon dioxide absorbs it and emits it in every direction. So this radiation gets trapped. So more carbon dioxide or greenhouse gases there is, more heat is trapped. And that's warming the Earth. Okay. All right, let's look at this number. How much heat are we trapping? Okay. Don't fall down from your chair. Okay, so we're trapping this much heat. This is about 100 times greater than the rate at which energy is used by all humanity. This is equivalent to exploding 20 atom bombs every second for how many days? All the time. That's how much heat you're trapping. Why? Because we've been using fossil fuels and we're putting more and more CO2 in the atmosphere. Okay, so in the 1850s, the amount of CO2 was 280 parts per million. Today, it's 425 parts per million or something like that. The more CO2 you put in the atmosphere, the more heat you trap.
So no more Hellcats?
I'm sorry?
No more Hellcats?
Hellcats? What are Hellcats?
Dodge's